Okay, so today we're going to continue on talking about acid-base theories. You've already read a little bit from yesterday's little reading assignment about the Arrhenius theory. I'm going to run through these slides very quickly because you should have this all written down. And then we're going to talk about something called the Bronstead-Lowery theory of acids and bases, and I'm quite sure I probably spelled that wrong on the lesson goals, but anyway, you'll get that figured out when we get to the note. In terms of acids and bases, we don't need to write this stuff down. We did check a few of these things. We checked the pH for acids lower than 7. We checked that they changed the indicator's characteristic colors, and you probably recall that they taste sour, and they're also electrolytes. We've talked about that as well. That means they conduct electricity in solution. And essentially, what are we saying here? All acids must have a common feature in order for them to have the same characteristics. You don't need to write that down either. We then, in the past, I've talked about just some common acids and bases, but we're going to just go past that because we've looked at some of them. And you should have written down that an Arrhenius acid are molecular compounds which ionize in water to produce H+. And that means that when the acid is put into the water, the H+ falls off, and then there's this H+ floating around. I wanted you to define ionization. Ionization is the process where a neutral molecule forms ions when dissolved in water. Now that's a little different than what we've encountered before, called dissociation, all right? Dissociation takes place when we have an ionic compound. They already exist as ions, and so when they go into the water, they simply separate away. That's dissociation. But a molecule like, say, HCl is a bonded molecule, all right? H, single bond, Cl, there's our Lewis structure. And so when HCl dissolves in water or goes into water, this bond is literally broken. And that when that bond is broken, it forms an H+ ion and a Cl- ion. In other words, the Cl gets the electron, and therefore ions are formed, and we call it ionization. So ionization is a little different than dissociation. There are some examples. I asked you to write some down in the book, and I'm not going to go through those. Properties of bases. Bases, again, change indicators of characteristic color. We saw that. They have a pH above 7. You should have measured that over and over again. They tend to taste bitter and are slippery to the touch. They are also electrolytes. And therefore, there's something in common. So what do they have in common? Well, they have in common this OH, the hydroxide ion. And so when we have something like sodium hydroxide, when it is dissolved in water, keep in mind, they're already ions. It's a sodium plus ion and a negative hydroxide ion. It ends up in Na+ and OH-. You might think this looks just like ionization, and it looks the same, but the sodium and the hydroxide were already ions, and so when they go in water, they simply separate or dissociate. No need to break a bond other than the attraction between the opposite charged ions. So, the OH is what Arrhenius believed was the important part of the base, and if something had OH, that made it a base. And there are some examples of some ionic compounds that have OH in them, and therefore, according to Arrhenius, these would be basic. Now, an Arrhenius definition of a neutral substance. You would have wrote down that when you copied down the chart. No need to write this down. And if you want to get this information, it is online. So it's something that dissolves in water but doesn't produce an H+ or an OH. Sodium chloride, Na+ and Cl-. When it dissolves in water, there's no OH or H+ produced. So according to Arrhenius, this would not be an acid or a base. We've also encountered molecules that are not ionic, that don't lose an H like an acid does. This OH here you might think is a hydroxide, but it's not. It's connected to these nonmetals. This actually falls in a category called alcohols. And when you put a molecule like this methanol into water, it simply dissolves. Bonds don't break. There are no ions in the water. It is not an electrolyte, and it is neutral if you were to check it with pH paper. So these are neutral as well. Now, There's some examples. Again, I'm not going to go through those. This is going to be an ionization. This is going to be a dissociation. Again, some more examples. This is going to be a neutral salt, and this is a neutral molecular substance. And that's the same homework that I assigned you as well. Problems with the Arrhenius definitions of salts. Let's not necessarily write this down. Let's just talk about it, and we'll get to the Bronstead-Lowery theory. It turns out that that Arrhenius, again, this is late 1800s, early 1900s. When scientists started to look at other acid-base properties of other compounds, they discovered that sometimes you could have a salt, which is an ionic compound, that when dissolved in water produced acidic or basic solutions. In other words, they did not contain any H plus or OH minus. Here we've got ammonium chloride. And NH3, the gas, ammonia gas. Here we've got sodium bicarbonate. Does not contain any OHs. And it turns out that this first one's a base, the second one is actually acidic, and the third one is also basic. And so some salts that should have been neutral were actually exhibiting some acidic and basic properties, which means there was something wrong with the Arrhenius definition. Essentially, Arrhenius said if it had H pluses and they came off in water, it was an acid, and if they have an OH and it comes off in water, it's a base. But it's not that simple. So we needed an expanded idea of what an acid and a base is. The reason, again, you don't have to write this down. The reason that Arrhenius's theory was incorrect is because he ignored the solvent. He ignored the water that this stuff was dissolving in. We now know that when an acid or a base is dissolved in water, it just doesn't fall apart and then exist on its own, but it actually interacts with the water itself. So the water is just as important as the acid and the base itself. And if we take into consideration the water molecules, when we analyze an acid and a base, then we get the correct observations. We get what is expected in terms of observations. So we need to bring the water into this theory. And you can hold on one second. You don't need to write this first one down, but you can put the title, please. Bronstead-Lowery Theory of Acids and Bases. And actually, I do want one bullet. I want that last bullet right there. The Bronstead-Lowery theory recognizes that in most acid-base reactions, a proton is transferred from one reactant to another. It's all about the H plus. And if we really think about that H plus, we will come to the realization that the H plus is actually a proton itself without any electrons. Hydrogen, diatom, one proton, one electron, sometimes has a neutron. That's isotopes. We won't worry about that right now. If we take that electron away and we turn that into an H plus and we remove its electron, we're now left with that. No electrons around it. Just the nucleus. Just the proton. All right? And it turns out that the study of acids and bases is really all about the study of what the proton does when it interacts in between chemicals. So it's really about the transfer and movement of protons from one substance to another. Okay? So let's now redefine acids and bases in terms of the Bronstead-Lowery theory. So a Bronstead-Lowery acid. A Bronstead-Lowery acid is a proton donor or an H plus donor. Something that can give up an H plus. In order to be a Bronstead-Lowery acid, it must contain an H plus that it can give up. HCl, H plus at the front end. There we've got phosphoric acid, H3PO4. That actually has 3 H pluses it can possibly give up. Doesn't always give them all up. You'll learn more about that next year. And so all of our acids, which have the H at the front, makes it the H plus. We put that positive ion at the front, just like the metals. So the H's at the front are acids, according to Bronstead-Lowery. And we'll just skip through this. Oh, no, we're not. We're going to have it run. Here it goes. There's my HCl. There's the water. Here it is. This is the excitement of animation. Watch it. Ooh. Did you see the donation of that proton? That was exciting. Again, one more time. The H2O accepts the proton. It becomes something called H3O plus. That's exciting. One more time. All right, one more time. Keep an eye on proton. There it is right there for all of you at home. Here it goes. Oh, got to continue. Here we go. Ooh. That's a donation of a proton if I ever saw one right there. All right, next slide. Now a Bronstead-Lowery acid isn't too far off of an Arrhenius acid. Arrhenius said it had to have an H plus, and it fell off. Bronstead-Lowery says it has to have an H plus, but it donates it. Now there's a slightly difference to that. Falling off of the H plus implies that the H plus then just floats around on its own. Donation of an H plus implies that there must be an acceptor of the H plus. And that's very important. And as you're reading right now, as you're writing here, the base is the acceptor. Something that accepts a proton is a base. Now that's really quite different than the Arrhenius theory. So somehow accepting a proton has got to result in OHs, because still OH is what makes our litmus paper blue. So what properties does an acceptor of a proton need? Well, a proton is short 2 electrons from a full orbit. It has no electrons, and it needs to fill the first orbit. So it's short 2 electrons. So any molecule that has a lone pair of electrons, we've seen the lone pairs, that proton can stick to it, make a coordinate covalent bond where the one atom has donated both and hydrogen's kind of latched onto that lone pair. And that then can result in acceptance of the proton, making it a base. It often also has a negative charge. A negatively charged ion will attract the proton to it. And if it also has a lone pair, it'll stick onto that. So negatively charged ions with a lone pair are fabulous at being a Bronstead-Lowery base. And let's watch some proton transfer one more time. Here we've got an NH3. Again, here we've got water. So let's see what happens here. Oh, ooh, that was exciting. This time we had the proton being donated from the water to the NH3. The NH3 being the acceptor that made it the base. In this case, the water donated it and it became an OH, which is good. That means that something like NH3, when you put it into water, in the end can produce some OH. That's still important. Even though we have this other idea now of what a base is, a proton acceptor, we never throw out the Arrhenius idea of the fact that a base somehow produces OH. That's still important in our theory. So we need to keep in mind the two theories together. And I'm going to show you how we keep that in mind. There is a way to use the Bronstead-Lowery theory to then in the end say, yes, this is basic. It's going to turn my litmus paper blue. Okay? We need to kind of put the two theories together. That's what we're going to do next. All right. So let's write down what a Bronstead-Lowery acid-base reaction is. Now, normally at this point, when I start doing Bronstead-Lowery acid-base reactions, I try to do them on the board. But because we've got a large amount of way for whatever, music, trip, something like that, I don't know. And they'll be the same this afternoon. I'm going to try to do this on the smart board. It's going to be a little jammed up in there, but hopefully we can see what's going on. If it doesn't work out, I'm going to the board, and all those people will just hear my voice, and too bad for them. Because we have to have a donor and an acceptor, we obviously have a transference of a proton of an H, which essentially is a chemical reaction. We're going to have reactants, then there's going to be a transfer, and we're going to have products. So we're now going to look at every little acid-base reaction as a little chemical reaction, as opposed to just ionization or dissociation. There's a little chemical reaction that has to go on. All right, let's take a look at some of these. So we've already seen the Arrhenius acid HCl. It's got an H on the front. Arrhenius would say, that's an acid. So how can we make this work in terms of a Bronstead-Lowery theory? Well, let's write the chemical reaction that's going to take place. So we're going to start with our HCl. And now we're going to react it with some water. Because we need to take into consideration what's happening with the water. Well, we already know that HCl is what? How would you classify it in terms of its acid-base properties? What is HCl? Yep, it's an acid. It's hydrochloric acid, so it's an acid, obviously. So this is the acid. And we can even call it the Bl acid, Bl, for Bronstead-Lowery acid. Now, I'm not going to write Bl all the way along here, but I am going to for the first couple. Well, a Bronstead-Lowery acid, what does it do with its proton? You got two choices, 50-50. It either gives it away or it accepts it. It's a donor or an acceptor. No keeping. No options that way. What do you got? It's a donor. So if HCl donates its H plus to the water, somebody tell me what the products to this reaction are going to be. Yep, John? I'm going to have an H3O, excellent, and it's going to have a positive charge because the H plus takes its charge with it. And what else is left? There's no Cl2. It is not chlorine gas. Cl, and it's got a negative charge. This is, again, a chloride, negative charge. Excellent. Well, if HCl was the acid, according to Bronstead-Lowery, what had to be the water? What was the water? What could we classify it? What do we have to classify it as? It's the base. It's the Bronstead-Lowery base. Bl base. Excellent. That's a Bronstead-Lowery acid-base reaction. Now, you might be saying to yourselves, wait a minute. Every time there's an acid, there has to be a base? Because every time I've got a donor, I've got to have an acceptor? And that's a true statement. According to Bronstead-Lowery, every time there is a Bronstead-Lowery acid, you have to have a Bronstead-Lowery base. Because if you're donating a proton must be accepted by something. There's no protons floating around there without anything. So next thing you might be asking is, well, if I have an acid mixed with a base, then this solution should be neutral. Because in the past, we've taught you an acid and a base makes neutral. But this is different. A Bronstead-Lowery acid is simply a donator of a proton. It has nothing to do with pH. It has nothing to do with the color litmus makes. It has nothing to do with the color your phenolphthalein is. It also has nothing to do with taste. It simply defines it as a donor of a proton. Same with a Bronstead-Lowery base. It's simply an acceptor of a proton. It has nothing to do with litmus, nothing to do with those tests. So how do we determine what kind of solution am I going to get? Because in the end, I can put some pH paper in that thing, and it's going to tell me something. So I need you to now know how to determine what that is. And the answer is right here. It turns out that it's not the H+, that's the thing that makes litmus red. It turns out that it's the H3O+ that makes litmus red. So what you need to do is you need to look at the products and you need to see if there's an H3O+. It's the H3O+, all right, that makes the solution acidic. Now, notice I've used ic on the end of acid. And I'm going to treat acidic completely different from acid. A Bronstead-Lowery acid is a donator of a proton. But something that's acidic makes litmus paper red, tastes sour, and will cause my pH meter to give a low number. So now when you see a product in a Bronstead-Lowery acid-base reaction that is H3O+, you can say, that's a good old-fashioned acid right there. That's going to make litmus paper red. It's going to make the pH meter give me a low number. It's going to taste sour. Okay? So that's what's telling you if that thing is an acid or is acidic or basic. I don't want to use is an acid anymore. I want to use makes an acidic solution. It makes it acidic. Therefore, litmus is red, pH is less than 7, etc., etc. It gives it the properties of the acid. Yep?
If, like, the quantity of H3O does that determine, like, how big?
Yes, it is. And that's going to be our calculations in another day or two. That's exactly right. Let's look at NH3. We saw NH3 in that little animation. Oops, I want green here. NH3, we're going to put it in some water. Now, NH3 could be a tricky one. It's got H's, but the H's are on the back end. So they're really not H+. They're actually H-. And so it might be tricky for you to say, all right, which way is this? What's going to be the donor? What's going to be the acceptor? It's difficult to say. Also, I just showed you a little video, little animation. What did the NH3 do? Did it, Connor? It accepted. What does that make the NH3? It's a Bronstead-Lowery base. I'm going to drop the BL. That's it. I've had enough. I'm dropping the BL. Sorry, couldn't resist. When I put base underneath, I want you to assume a Bronstead-Lowery base, that it's an acceptor. Well, if it's the base, what's water automatically? Yep. It's the acid. You got to have them. They're together. The acid. All right. So now it's accepting. It's donating. You got to think it through. What are my products? What's that water going to turn into, et cetera, et cetera? Yep. Yeah, I'm going to have an NH4. Don't forget that the H brings its charge with it. And OH-. Excellent. Well, you tell me. If I put litmus in this thing, or if I check it with a pH meter, or whatever, Is this thing going to be acidic, basic, or neutral? What's this going to be? Basic. Why would this be basic? Nope. It's not the lack of an H3O. Yep. It has the OH as the product. So the OH needs to be a product in order for it to be a basic situation. So in this case, when you get an OH as a product for a Bronstead-Lowery acid-base reaction, then this is, right, the solution is basic. OH minus, it's the best base. We can even have OH minus as a reactant. It will always be the Bronstead-Lowery base. OH minus is the base of all bases. H3O plus. It can also be a reactant. I'm going to put it as a reactant a little later on. It's always an acid. H3O plus is the best acid. All right? It's what defines our acidic and basic scenario. Therefore, litmus blue, pH greater than 7, etc., etc. Bitter, all that stuff. All right? Let's now try a couple of other scenarios and see if we can now make some predictions on whether it's going to be acidic or basic or whatever. So now we've got the the basic ideas. Sorry. All right. Let's take a look at NaOH. We already have this down as being an Arrhenius base. It's got an OH on the back end. So let's see if we can reconcile this with, what we now know. This here is ionic. And if you're starting with an ionic compound, you first have to dissociate it. In other words, separate into its ions. And then we need to take a look at what those ions are going to do in the water. Therefore, dissociate it first. You always do that when given an ionic compound. So, NaOH, we're going to put it in some water. It's aqueous. What do I get? This is really straightforward. Nothing magical here. What does that fall apart to, Tim? Yep. Na plus OH negative. Now, one of those things is going to react with the water. The other one is going to do nothing. Which one is going to do nothing?
Sodium.
Yeah, why sodium?
Because it's plus in the critical reaction.
Okay, I don't mind that idea. It's the plus, and an H plus isn't going to necessarily be attracted to that plus. That's pretty good. And the OH is a minus and therefore can react. That's okay. Why else might sodium do nothing? Ideas? You need a base in this reaction because it's got to be basic, right? And therefore, I need an acceptor, and that OH would be a great acceptor. I like that answer as well. I like that answer as well. Let's think of this in a slightly different fashion. We've encountered sodium many times. We've encountered it on the solubility table, and we've also encountered it in something called net ionic equations. What's sodium notorious for on our solubility table? Being a spectator. Poor sodium, always at the dance, but on the sidelines. And that doesn't change here. Sodium will take the OH to the dance. The OH will go off and hang out with the water molecules, and sodium's going to be a spectator because it always is a spectator. And so spectators don't undergo acid-base reactions because they're just not, they're just not attracted to the things. So this thing we would say is a spectator. All right? So we are not going to include the spectator in the reaction with the water. So now what do I have? I've got, whoops, I wanted that to be green again. I've got OH minus plus H2O. And what are the products going to be of this thing? Kind of silly, isn't it? What are my products going to be? Yep. Yeah, H2O and OH minus. H2O plus OH minus. The OH minus came along, bumped into a water. Hey, I like your proton, thanks. Whoop. Took it away. Yay, I'm water again. Woo! Scurried off. The water molecule stand there. What? I was water a second ago. Now I'm hydroxide. Jeez. Gonna make the litmus blue. That's okay. That means in the end, we have this stuff. Therefore, what's the solution? Basic. Now, you might think, well, that was dumb. We knew it was basic in the beginning. But we needed to explain it in terms of the Bronstead-Lowery theory. Again, we can assign all of our important labels here. This is the base. This is the acid. Okay? Now, this actually brings me to a point where I can introduce to you a couple of other terms. It turns out that these reactions can actually go backwards as well. There's no reason why that poor water that recently became the hydroxide doesn't chase down that water molecule. Hey, come back here. Give me that. Wrestles its proton back. Turns back into water. And the base turns back into the base. And it doesn't even have to be the same water molecule. Now you can imagine that this game for the proton becomes quite complicated and convoluted. And I like to imagine it as a game. You can imagine it either as a hot potato game, because if you're an acid, the goal of your life is to get rid of your proton, to be a proton donor. So as soon as you get in the water, what do? Whoop, give away your proton. Yay, I win. If you're a base, then it's one of these keep away games, right? Whoop, I got your proton. Yeah, whoop, run away. Now the game doesn't stop. You put it in the water, it's not like it transfers once and then some, referee blows the whistle. All right, game's over. Who's got the proton? Right there. Yeah, you win. Good job. It's like the game continuously goes. That OH that's been formed can now bump into a water, take the proton. Yeah, I'm water. New hydroxide. I'm going to get proton. Grab the next proton it sees. And that reaction goes on and on and on and on. And there is no referee. The only way you can stop the game is if you were to put some extra protons in, neutralize the OHs, and make them all back into waters. It's the only way you can stop the game. So now when you look at a base, or even an acid, in there, there's a game going on. And it's continually going on. There's protons being transferred over and over again. Now that's interesting. That means if this reaction can continue on, then now I can reclassify my newly formed water as an acid. It's going to be able to donate to this guy. We call this the conjugate acid. And it's going to become an important term in a moment. Right now, the conjugate acid is the same as the other acid. But for a regular reaction, it isn't. Conjugate just means opposite. It means once it was the base, it then became the conjugate acid. So a base, once it's gained a proton, becomes its opposite acid. Pardon? The base gains a proton and becomes its opposite acid. Its acid is going to then become a conjugate base. Yes. You have two acid-base pairs, always. We'll look at more at this in a moment. All right. So let me just write a little definition down here. Conjugate, and I'm going to put acid, all right, is essentially like the opposite. What did I do? Conjugate What have I done? Oh, don't be so mean to me. Acid. I'm worried about spelling that word. It's the opposite. Opposite. Now I'm going to spell opposite wrong. Opposite, acid. Jeepers creepers. We'll talk more about that in a minute, because now my feelings are hurt. All right. NH3 plus HCl. All right. I'm going to rewrite it down here. NH3 plus HCl. What if we put some NH3 together with some HCl? This can all be in water as well, right? You can mix them together. We've encountered HCl and we've encountered NH3. So somebody tell me what's going to happen. I'll take the products. You can tell me what the acid is and what the base is. It's up to you. Let's take some information here. What do we got? Yep. So we're going with NH4 plus Cl minus. I like that. Now let's put some labels under these things. What was the NH3? The base, the acceptor. HCl? Once you know one, you've got the other. Acid. All right. What's NH4? It's conjugate something. It's a good start. Conjugate acid. The base became the conjugate acid. Conjugate acid and conjugate base. All right? Which means now, if this happens in water, there could be some interesting things going on in there. They could behave as acids and bases, but we're not going to worry about that right now. All right? So that's, and if these things were in equal amounts, would this mixture get us acidic, basic, or neutral? What would it get us? Any ideas? It's a tricky one. Actually, I shouldn't even ask the question. The answer I expected to give me is neutral. But this one isn't really neutral. I'll talk about maybe why that is a little later on. But why would you think that this is neutral? Nope. Nope. Look at the products. Nope. What's that? There's no OH or H3O+. There's no OH or H3O+. Now, it turns out that one of these products can also react to produce an OH or H3O+. We'll talk about that later. But in this case, at this point, it looks like it could be neutral. But there's an extra step that we can do in a moment as well. All right. So now that we've got this idea of what a conjugate acid-base pair is and how they transfer their protons, we can now look at one of the problems of the Arrhenius theory. We can look at why some of our salts are not neutral. Now, you haven't gotten down to the example yet. Just put EG so we can shorten things up. And the example is, sodium NaF. And we're telling you it forms a basic solution. We're being nice here. That's okay. You guys are just new at this theory. NaF is an ionic compound. What do we do when we have an ionic compound? Before we can look at the reaction with water, what's the first thing I had to do? separate it, dissociate it. That's what it says in A. First dissociate it. I already told you to do that. NaF is going to become Na plus F minus. Now, the person who made the note is telling you which one's going to react, but you could have determined that. What do we know about sodium? It's a spectator. It's not going to do anything. That thing's spectating. So it's going to be the fluoride that reacts with the water. So the fluoride is introduced into the water. And we've already told you that it makes a basic solution. But if you take a look at this F minus, the H plus is definitely going to be attracted to that F minus. So what are the products going to be? Yep. HF plus OH minus. Let's put our designations underneath them. What then was the F? What was the F behaving as? Connor, you got an idea there? The base. You bet. Base, acid, conjugate, acid, conjugate, base. Now, again, new students, when looking at this theory and looking at the products, are sometimes tricked a little bit in thinking that maybe this should be an acidic substance because it's made this conjugate acid. But remember, the conjugate acid just means that it's something that has the potential to donate. But I've already told you something very important about the OH. The OH is the best base. It's a better base than this thing is as being an acid. So that's going to be a basic solution. If you have OH as a product, it's going to be basic. Therefore, it's basic. Okay? Let's do one more of these guys. Ammonium chloride. Again, we just actually encountered an ammonium chloride scenario. NH4Cl. Dissociate it. Getting NH4 plus Cl minus. Now, you haven't been given this information yet. We kind of know it a little bit if we take a look at our solubility chart. And if you take a look at chloride, you'll see for pretty well almost everything except silver, chloride is a spectator. Yep, minus charge, sorry. And it turns out that chloride is also most often a spectator. You can assume that. You can assume if you get chloride that it is a spectator. Yep. Talking and thinking all at the same time. It's very dangerous. Maybe I should try talking, thinking, texting, and chewing gum at the same time. Be catastrophic. Be instant death. Don't try that. Your brain would explode. It would be horrific. Well, my brain would explode. I don't know about your brain. People keep telling me times are changing. Maybe your brains are better than my brain. Okay. Chloride is pretty well almost a spectator. It's like the negative equivalent of the sodium, except with the odd ion, which means we'll be dealing with the NH4. Now, I don't want to go back in my PowerPoint because I'm afraid I'm going to lose my writing. But if you go back and you look at the products of the reaction between the HCl and the NH3, we also obtained an NH4 plus and a Cl minus. Now, there was no OH or H3O plus, so I said that you would think it was neutral. And if you answered neutral on test and gave me the argument that there was no H3O plus or OH, I'd say at this level, yeah, that's good logic. That's correct. But in reality, if there's NH4 plus and Cl in the water, then the Cl is a spectator, and that NH4 plus will react with the water. And what products am I going to get here? We're always moving only one H plus when we do these reactions. Yep. Yep. NH3 plus H3O plus. And therefore, when those two things are in the water, NH4 and Cl minus, this ends up being acidic. All right? So that's kind of a neat little result that comes from that. Okay? Oh, let's label these up. What is my NH4 acting as? Go ahead, yell it out. The acid. Acid, base. This is the conjugate. What's this? Conjugate base, and that's the conjugate acid. And again, H3O plus, it's the best acid. It's always going to be an acid, whether it's conjugate or otherwise. Amphoteric or amphiprotic substances. Now just some definitions to finish this all off. All I need to do is give you a handful of definitions and things, and then we've got it covered. Let's just put here, for example, C above. Put water and then put C above. All right? Don't write down the examples. We've had many examples where water is the donator or water is the acceptor. And so water can be both a Bronstead Lowery acid or base. Don't write these examples down. We've got a million of them. I'll just complete it quickly. H3O plus NO3 minus. There it's acting as the acceptor. So this thing is the base. All right. Here we just saw this reaction earlier on. This would then be HF and OH minus, and there it's acting as the acid. Don't write those examples down. We've got a bunch of examples of water up above being amphoteric or amphiprotic. It can accept or donate. Okay? Let's talk about one other important amphiprotic or amphoteric substance. The bicarbonate ion. All right? And the bicarbonate ion can come from sodium bicarbonate. NaHC, CO3, that was horrendous. And when it dissociates, I get NH plus HCO3 minus. And sodium bicarbonate is also known as baking soda. Baking soda. Baking soda is a great super chemical. It's awesome. We've already seen it once. When you heat it up, it decomposes. Some of you found it made sodium carbonate, but it always, for whatever the reaction was, carbon dioxide and water, which means it's great for putting out a grease fire. You spread it on it, it decomposes, it makes carbon dioxide, the carbon dioxide smothers the fire, puts the fire out. Always keep some sodium bicarbonate nearby. Not only does it put fires out, but let's say you're unclogging your clogged drain, and you're using some super-powered Drano or something like that, and as you're getting ready to pour it down the drain, you trip and fall, and you spill it all over the floor. Well, it turns out that those drain cleaners contain concentrated sodium hydroxide, which means it's quite dangerous to just clean up with your hands. You'd end up with base burns on your hands. Never fear. You go for your box of your super chemical, your baking soda, and you sprinkle it on top of that. Because if you do so, this sodium bicarbonate, because it has this negative charge, because it has an H on it, can transfer that H. This can behave as an acid to the awesome baseness of the OH, because it's the best base. What are the products going to be of that? Transfer the H, 1H plus. We're moving it over again. Emily. H2O plus CO3 minus, and the OH is gone, and you've neutralized the base. You've gotten rid of it, and it's safe now to clean up. All right? And once you clean that up, you're going to take your Bowl Bright. You can buy it. It's called Bowl Bright. It takes rid of iron stains. If you have iron in your water, you can clean the toilet bowl, hence Bowl Bright, or whatever surface that's stained with iron. It contains some concentrated sulfuric acid. And again, you're clumsy. You trip and fall. And you spill your Bowl Bright all over the place. Concentrated sulfuric acid. Don't clean that up with your bare hands. It's going to give you a burn. Trust me, I've done it before. So what do? You go for your super chemical again, and you sprinkle some sodium bicarbonate on that. Again, the H3O plus that was in the sulfuric acid is the best acid ever. It's always going to be the acid. But because of the negative charge on the bicarbonate, it can also be an acceptor. And what are the products to that transfer? H plus, transferred again. Connor, you got it mastered? H2CO3 plus H2O. And are there any H3O pluses left? No, it's neutralized and you are safe to continue. Actually, H2CO3, we've seen this in the past, this can decompose into H2O liquid and CO2 gas, and so that actually fizzes away and is gone in the end. So it's done its job, it saved the day, it's neutralized the acid, and it's turned into carbon dioxide and water. But sodium bicarbonate is amphiprotic or amphoteric because depending on what conditions it's in, it can be a Bronstead-Lowery acid or a Bronstead-Lowery base. Don't write this down. Make reference to it if you want. This is defining conjugate acid-base pairs, but I've already told you about this, right? Here we've got a reaction with something called acetic acid. And it's this last H that's the acidic H for this one. This one gets transferred here. We get H3O plus, and then we get the acetate ion. But the reverse reaction can happen. I already told you about this, that this can bounce back and forth. There can be this keep away or hot potato game that goes on with the proton. And so an acid on one side can become a base on the other side, the conjugate or opposite base. So I don't think we need to write this down. We've talked about conjugate acid-base pairs. It's there. A conjugate acid-base pair, actually, let's maybe write this one down officially, because I didn't write down officially what a conjugate acid-base pair is. But it's the pairing of the base becoming the acid and the acid becoming the base. In this case, the 1 and the 2 simply represents the first pair and the second pair. All right? Again, that's kind of a review of what we've kind of just talked about. Nothing earth-shattering on that slide. Okay? Are you good to go? You're just saying that. Don't mind that. Now, don't write these questions down. Let's just work through them together. And then I'm going to give you all kinds of them that are just like it. And don't worry about writing them down as examples. I'm going to put it up online. You can always go back and look at it. Let's just get through it so I can give you some practice ones to work on. Identify the conjugate acid-base pairs in the following reaction. Well, my eyes would go straight to this. What's that? It's the best base. It's not just a base, man. He's the awesomest base.
For all students wearing yellow, please go to gym AB for the suicide awareness photo access.
If you'd like to go to such a thing, by all means, take one of these pieces of paper. I'm going to continue on and quickly finish this off. All right? Anyway, what does that make this guy? Acid. What does that make this guy? I'm going to keep going to Emily because I want to finish this. That makes this the base, and this becomes the acid, and the conjugate acid-base pairs then would look like this and like that. Okay? Again, please take a sheet before you go. Taking a look at this, again, I'm going to keep talking like I got a class in front of me because I'm taping and I want to finish it. Given this as an acid, what's its conjugate base? If it's an acid, is it a donor or an acceptor, Connor? An acid is, it's a donor, right? It's a donor. If this thing is giving away an H+, what's it going to become? OH-. OH-. I wanted green, that's okay. All right? If this is a donor, what's it going to become? It's going to get rid of an H+. So it's going to get rid of an H. Megan, what's this going to become when it gets rid of an H? It's going to be H2PO4. And if the H took a plus charge away from it, plus charge away from it, what must be the charge of the thing that's left? A minus. Very good. HS-. If it's an acid, what's going to be left when it's done doing its job? Emily? S. And what's the charge going to be? It is a minus to begin with. It's given away an H+. Now what's it going to be? Phil? -2. Because it went from -1 to -2 when it gave that charge away. There's the other side of it. Let's say the water is behaving as a base. A base is an acceptor. What's it become? Connor? H3O+. Base, an acceptor. Rachel, what's that going to become? H2SO4. No charge, because the negative and positive canceled out. And if that's a base, what's it going to become as an acceptor? Megan? What charge? It's going to bring a plus with it when it gains it. NH4, this guy's a plus. All right? Okay. I don't know what the homework says on the sheet. It doesn't have all of that. It has some of that. This is extra. You can write that down, and I'll hand this out. And I'm going to stop this right here before we get